Hello, welcome to Unacademy. Today we will see how to evaluate the complex integral by using Cauchy's residue. In last lecture we have seen the integration or how to evaluate the complex integration by using Cauchy's integral theorem as well as by using Cauchy's integral formula. Okay. We will see here. And before going to start this, let me and some example we will see on this complex integration, how to evaluate the complex integration by using Cauchy's integral formula, Cauchy's integral theorem, as well as Cauchy's residue theorem. Okay, लास्ट लेक्चर हमने पढ़ा है कि Cauchy's integral theorem से और Cauchy's integral formula से हम लोग कॉम्प्लेक्स इंटीग्रेशन कैसे इवेल्युएट करते हैं. इस लेक्चर में हम लोग देखेंगे कि कॉम्प्लेक्स इंटीग्रेशन हम लोग बाय यूजिंग रेसिड्यू थ्योरम कैसे करते हैं or Laurents series and Taylor series. Okay. And after that we will take some examples and you have to think out which formula or which theorem is applicable to evaluate the given complex integral. Okay. So let's start. Before going to start this, let me introduce myself. Myself Dhanashree Mam. I completed my MSc in Mathematics from Mumbai University and also having 13 plus years of teaching experience, and I mentored more than 10,000 plus students for the engineering. Now, I'm giving you brief here how to install the Unacademy's Learning app. First, go to your mobile's Play Store app, then search Unacademy's Learning app. Then after that, install the Unacademy's Learning app. After that you have to manage your goal. So how to manage your goals, जैसे कि हम लोग यहाँ पे अभी GATE and ESE के लिए पढ़ रहे हैं. So that here हमने goal manage किया हुआ है GATE and ESE. So it's like you can manage your goal here and take any one of the subscription, either plus subscription, free subscription or special classes. And after that press the get subscription button. So the next step is see for कितने टाइम के लिए आप सब्सक्रिप्शन प्लान लेना चाहते हो. यहाँ पे आपको प्लान सिलेक्ट करना है जैसे कि 24 मंथ्स है, 12 मंथ्स है, एनीथिंग. और यहाँ पे आप लोग मेरा अगर इफ यू वांट टू take a subscription plan and if you want 10% discount on your subscription fees, then you can use my promo code, that is DSP, so that you will get a 10% discount on it. And the next point is you can pay your subscription fees by using any one of this method, either by debit card, credit card, EMI, UPI, anything. Now, let's start our actual topic, that is Taylor series. Now see Taylor series, let A0 plus A1 into Z minus A plus A2 into Z minus A bracket square plus and so on, N into Z minus A bracket raised to N plus and so on, which is equal to summation n varying from 0 to infinity an Z minus A bracket raised to N. So summation n varying from 1 to 0 to infinity and n into Z minus A bracket raised to N is called the power series in Z minus A. So see here the binomial series 1 plus Z bracket raised to N and so on. This is valid for mod of Z is less than 1. We will use this series also. Is your binomial series, and 1 plus Z bracket raised to N is equal to 1 plus NZ plus N into N minus 1 by 2 factorial into Z square plus N into N minus 1 into N minus 2 upon 3 factorial into Z cube plus and so on. Valid for mod of Z is less than 1, or mod into 1 minus Z bracket raised to minus 1 is equal to 1 plus Z square and so on plus and so on. So here if we use put n is equal to minus 1 and here is minus 1, so you will get this series, all the terms are positive, and if you put here plus, then ascending power of this. So binomial expansion of this series 1 plus Z bracket raised to minus 1 and A upon 2 factorial into Z minus A bracket raised to 2 plus F triple dash of A into f triple dash of A upon 3 factorial into Z minus A bracket raised to 3 plus and so on. That is power series converges of f of z when mod of z is less than r. This is known as Taylor series of f of z about z is equal to A. हमने टेलर सीरीज अबाउट एच, अबाउट एक्स, ये सब कुछ पढ़ा है। तो यहाँ पे हम लोग यहाँ क्या करेंगे, टेलर सीरीज with complex numbers. F of z is analytic function inside the circle C with center at z is equal to a and radius r. Then each point inside C is f of z is equal to f of a plus f dash of a into z minus a upon 1 factorial plus f double dash of a upon 2 factorial into z minus a bracket square plus f triple dash at a upon 3 factorial into z minus a bracket raised to 3 plus and so on. That is power series converges of f of s when mod of z minus a is less than r. Okay. Now, this is known as the Taylor series of f of z upon z is equal to a. Okay. Now see here, you can see now the expansion is valid. The expansion is valid at all the points interior to any circle having its center at A and circle is known as the region of the convergence. Put A is equal to 0. The series becomes f of z is equal to f of A is equal to 0. So here f of 0 plus f dash of A plus here is f dash of 0 instead of A. F dash of 0 into z upon 1 factorial plus f double dash of 0 into z square by 2 factorial plus f triple dash at 0 into z cube by 3 factorial plus and so on. Okay. Now we'll see how to evaluate this. Now next, Laurents series. If f of z is analytic inside C, then f of z can have always represented by a power series in the power of z minus a, that is about a point A. But then at each point z in R, f of z can be represented by f of z is equal to a0 plus a1 into z minus a plus a2 into z minus a2 into z minus a bracket square plus and so on a minus 1 z minus a bracket raised to minus 1 plus a minus 2 z minus a bracket raised to minus 2 plus and so on, which is equal to summation n varying from 0 to infinity n into z minus a bracket raised to n plus summation n varying from 1 to infinity n minus n z minus a bracket raised to minus n is called a power series in z minus a. Okay, this is called as a power series in z minus a. Now the series contains a series consisting of a powers of z is equal to z0 is called the analytic part or Taylor's part of a Laurents series. The series consisting of negative powers of z is equal to z0 is called the principal part of a Laurents series. Now where n is equal to 1 upon 2 pi I into integral close integral over c f of z upon z minus a raised to n plus 1 dz, where n is varying from 0, 1, 2 and so on. And n at minus n is equal to 1 upon 2 pi I close integral over c f of z upon z minus z raised to n plus 1 dz, where n varying from 0, 1, 2, 3. This is called as principal part of the Laurents series. No, the part summation n varying from 0 to infinity n into z minus a bracket raised to n of Laurents series is called the Taylor's part, and the part summation n varying from 1 to infinity n minus n z minus a bracket raised to n is called the principal part of f of z. In the Laurents series, f of z is not analytic inside C1. If f of z is analytic inside C1, then n minus 1 is equal to 0 and n is equal to f raised to n at a upon n factorial, and the Laurents series reduces to Taylor series. Okay? And the Laurents series reduces to Taylor series. Now we will see expand. Here expand z minus 1 upon z plus 1 in the Taylor series about z is equal to 1. Very simple example. We will expand this about z is equal to 1. So here our Taylor series is defined as, yeah, Taylor's series defined as f of z is equal to f of a plus f dash of a into z minus a upon 1 factorial plus f double dash of a into z minus a bracket square upon 2 factorial plus f triple dash of a into z minus a bracket raised to 3 upon 3 factorial plus and so on. Okay. Now here we have to expand about z is equal to 1. Okay. So we will expand this about z is equal to 1. So here your f of z is equal to z minus 1 upon z plus 1. Right. So for that we require f dash of z, f double dash of z, f triple dash of z and so on. So we will calculate f dash of z here. For first of all we will write f of z. So here f of z is, we'll get f of z is equal to here z minus 1 upon z plus 1, right? So f dash of z, what will be your f dash of z here? You will get f dash of z is, therefore here f of 1 is equal to, put f of 1. So 1 minus 1 0, so f of 1 0. Now you will get f dash of z. F dash of z is what? P du, so z plus 1, so derivative of z minus 1 is 1 minus z minus 1 into derivative of z plus 1 is for z plus 1 bracket square. So we require here z plus 1 and minus of z plus, minus of minus plus 2 plus z minus z cancel out, and this minus minus of plus 2. So 2 upon z plus 1 bracket square हो जाएगा, right? F dash of z is equal to 2 upon z plus 1 bracket square. Now we will get f dash of 0. Because sorry, f dash of 1. So you will get f dash of 1, put z is equal to 1. So 2 upon 1 plus 1 2 z plus 1 or 1 z plus 1 and z plus 1 bracket square, that is z raised to 4, that one get cancelled out. So minus 4 upon z plus 1 bracket cube. Okay. So you will get here minus z plus 1 minus 4 upon z plus 1 bracket cube. So f double dash of z is equal to this. Now calculate f double dash of 1. We will get f double dash of 1 is equal to minus 4 upon, put z is equal to 1. So z is equal to 1, 1 plus 1 2, 2 cube is 8, minus 4 by 8, that is minus 1 by 2. So f double dash of z is equal to minus 1 by 2. Now, so f triple, so by Taylor's theory, f triple dash of z, you can calculate f triple dash of z, z plus 1 bracket raised to minus 3 becomes that minus of minus 3, so plus 12 into z plus 1 bracket raised to minus 3 minus 1 minus 4 from z plus 1 4, right? So you will get 12 upon z plus 1 bracket raised to 4, triple dash at 1 is equal to, put z is equal to 1, so 1 plus 1, this 1 plus 1 becomes 2, 2 raised to 4, this 12 upon 2 raised to 4, 2 raised to 4 is 16, the 4, 4 to z into 16, 2 raised to 4 by 4 is 3 by 4. Just put the value, all the values of f of z. This will get your f of z is equal to f of a. F of a is 0, so that is 0. And then f dash of a. F dash of a upon z minus a. So z minus a is z. Dash of a is 1 by 2. So z by 2. So here is z minus 1 by 2. Z minus 1 by z. Right? Z minus 1 by z minus 1 by 4 minus 1 by 4, because 2 into 2 factorial, that is 2, minus 1 by 4 into z minus 1 bracket square plus 3 by 4 into z minus 1 bracket raised to 3 plus and that's, this is your Taylor series. about z is equal to 1. I hope clearly understood. Now find the Laurent series of f of z is equal to 1 minus z square with the center at z is equal to 1. Okay. With the center at z is equal to 1, it means it's the circle with center at z is equal to 1, or the circle here with center at z. Yes, is also the circle with center at 1. This one 0. Obviously radius is also 1. Get the radius is 1. Let z equal to 1. Of z is equal to 1 upon 1 minus z square. Can I write this as 1 minus z square? So in the Laurent series, we want to find out the n and n of minus n. So that your series expand in this way, 1 upon 1 minus z square. So can I write this as 1 upon 1 minus z to 1 z will become 1 upon x minus or 1 2 minus 1 by 2 by 2 bracket upon z minus 1 plus 1 by 2 into bracket 1 upon z plus 1. Okay. 1 upon z square is 2 minus 1 plus 1 by 2 into 1 upon z plus 1. Right? Now this is your 1 upon 1 minus z square. No. So we will get here expansion of, so 1 upon z. So can I write this as 1 upon z into z minus 1 bracket minus 1 plus 1 by 2 into bracket z plus 1 bracket minus 1. So use the binomial expansion here. So z minus 1 bracket raised to minus 1 and z plus 1 bracket raised to minus 1. Okay. So you will get here z plus 1 instead of this is 1 plus 1 by 2. We'll get here z minus 1 minus 1 by 2 into bracket minus 1 bracket minus. So this plus 1, can I replace this plus 1 as 2 into z minus 1 plus 2? Here is, we can write 1 upon 2 into z minus 1 plus 1 upon 2 into bracket z minus 1 plus 2. Right? Why I'm writing the same. Instead of writing z plus 1, I'm writing z minus 1 plus 2. But what it indicate, which is equal to, there is minus 1 upon 2 into z minus 1 plus 1 by 4, taking 2 common. Here you will get 1 because 1 plus z minus 1 by 2 bracket raised to, because ultimately it is we have to convert into one either in the form of 1 plus z or 1 minus z. Okay, so for that 1 plus z, convert it into 1 plus z, I am converting in this way. Or you can take the minus, you can take here z common, 1 plus 1 by z is also okay. Both the ways are there. 1 minus z minus 1 by 2, as it is plus, so it is alternate plus minus plus minus plus minus 1 bracket square 1 by 2 brackets plus minus z minus 1 upon 2 bracket plus and so on. We'll get here valid for, this is valid for 0 is less than mod of z minus 1 is less, okay, because only inside the circle, okay, because mod z is equal to 1. Third is valid for only mod of z minus 1 is less than 2. Is valid only for the mod of z minus less than 2. Your Laurent series. Hope you are clear. Find the Laurent series for f of z is equal to z minus 3 into sine of 1 upon z plus 2. About z is equal to minus 2. Right? So z is equal to x minus 2. Right? F of z and is equal to x minus 2. Get x minus 3. So here x minus 5. Right? To sine 1 upon z is equal to x minus plus 2 minus 2 get cancelled out, which is equal to x minus 5. Now the sign expansion, and series we'll get here 1 by x on factor to x raised to 5 plus on 5 factorial into x raised to 5 plus and so on, which is equal to x minus 5 by x minus x minus 5 by 3 factorial is 6, right, as it is. Only 3 factorial into x raised to 3 plus x minus 5 upon 5 factorial into x raised to 5 to x raised to 5. And so this is your f of z. Ultimately you can write f of z is equal to x, so minus 5 by here 1 minus 5 by x, right, f of equal to 1 5 by 3 factorial is 6 square upon x, so x upon 6x square 1 upon 6x minus plus 6 upon x, get here square plus so on of z is equal to just x, get minus x is equal to x is equal to z plus 2. 5 upon z plus 2, it means 5 into z plus 2 raised to minus minus 6 into z plus 2 raised to 2, right? So z plus 2 raised to minus plus 5 by 6 to z plus 2 raised to minus. The Laurent series. Hope you clearly understood how to find out the Laurent series expansion. It is always in terms of that mean by pole. Yesterday also we many times we used the pole z is equal to a. तो ये pole है क्या? The pole, the principal part of a Laurent series contains a finite number of terms. That is the series a minus 1 z minus a raised to minus 1 plus a minus 2 into z minus a raised to minus 2 plus and so on a raised to minus n into z minus a raised to minus n consist finite number of terms, then z is equal to a is called the pole of order n of the function f of z. Okay, z is z minus a raised to n, then z is called as z is equal to a is the pole of order n. ये आपका pole. Now there are two types of poles. First simple pole and pole of order n. अभी simple pole क्या है? If the principal part of a Laurent series contains only a minus 1 z minus a raised to minus 1, then z is equal to a is called a simple pole. 1 minus z minus a raised to minus 1, it means it is 1 upon z minus a, right? So it is a simple pole, and raised to minus n, it means raised to n. Raised to minus n, it means 1 upon z minus a raised to n. तो ये हो गया z is equal to a is a pole of order n. अगर यहाँ पे 1 है तो only you can say that z is equal to a is a simple pole. ये order अगर 1 आ रही है then z is equal to a is a simple pole. The calculation of residue. How to calculate the residues, right? How we will calculate the residues? First, if f of z, if f of z is a pole of order 1 at z is equal to a, then residue of f of a is equal to limit as z tends to a at z minus a into f of z, which is equal to z minus a into f of z at z is equal to a. सिंपल, जो भी a है पोल है, z को हम लोग लिमिट लेंगे, लिमिट एट z टेंड्स टू a, तो z ऑफ z minus a into f of z, which is equal to z minus a into f of z at z is equal to a. Now third, second one, if the f of z has a pole of order n greater than 1, जैसे कि मैंने अभी बोला, अगर यहाँ पे पोल ऑफ ऑर्डर 2 भी है तो हम लोग यही रूल अप्लाई करेंगे फॉर कैलकुलेशन ऑफ रेसिड्यूज. देन रेसिड्यू ऑफ f of a is equal to limit as z tends to a 1 upon 1 n minus 1 factorial, so d raised to n minus 1 upon d z raised to n minus 1 and into z minus a raised to n into f of z. Okay, so is equal to 1 upon n minus 1 factorial into d raised to n minus 1 upon d z raised to n minus 1 into z minus a raised to n into f of z raised to f of z at z is equal to a. See the residue theorem. What do you mean by residue theorem? We will use that residue theorem here. So f of z is an analytic function within a simple closed curve C, except at a finite number of singular points. Singular points हमने कल देखा है. What do you mean by singular point? अगर उस point के लिए function is to be analytic, then that is your singular point, right? So if a1 a2 up to n, say in the side C, then इंटीग्रल ओवर सी एफ ऑफ जेड डी जेड इज इक्वल टू, हम लोग अलग अलग रेसिड्यू निकालेंगे हर एक पॉइंट के लिए और वो ऐड करेंगे एंड मल्टीप्लाई करेंगे विद रिस्पेक्ट टू, और यहाँ पे मल्टीप्लाई करेंगे 2 पाई आई को, तो मिल जाएगा हमें रेसिड्यू थ्योरम इंटीग्रल ओवर सी एफ ऑफ जेड. मतलब सपोज दिस इज योर क्लोज्ड कर्व सी है और ये हमारे सिंगुलैरिटीज है a1 a2 a3. These are our singularities for different n number of points. So we can calculate the residue for each point depending upon whether it is pole of order 1 or a pole of order greater than n is greater than 1. Okay, so this residue is depending on this, that is equal to 2 pi I into sum of the residues at z is equal to a1 a2 up to an, a1 a2 a3 up to an. Okay. Now you have to remember these things while solving any example on complex integration. Okay, अगर आप कौन सा भी एग्जाम्पल सॉल्व कर रहे हो कॉम्प्लेक्स इंटीग्रेशन पे तो आपको ये याद ही रखना है क्या है, इफ द पोल लाइज आउटसाइड द गिवन कर्व C, then the Cauchy's integral theorem, then use Cauchy's integral theorem. अगर हमने कल ही देखा है, अगर क्लोज इंटीग्रल है अपना हमारा यहाँ पे क्लोज इंटरवल है, राइट, क्लोज्ड कर्व दिया हुआ है C, अगर if your point z is equal to a lies outside the curve C, then directly without doing any calculation you can write down for that Cauchy's integral theorem, the value of the integral is 0, right? And if the pole z is equal to a lies inside the curve C, then use Cauchy's integral formula or Cauchy's residue theorem, whatever it is. Cauchy's residue theorem for the simple pole or if it is of order n. And if there are finite number of poles, जब z is equal to -1, z -2, z -3, z -4 है तो obviously you have to use the residue theorem to find out the integral, complex integral. We have to use the Cauchy's residue theorem if there are finite number of poles are given. Okay, So these things are very important. So find the residue according to the pole, simple pole or pole of order n. Okay, so these 4 points are very important while solving any example on complex integration. Now let's see our first example. Find the residue of z cube upon z minus 1, z minus 2, z minus 3 at each point. यहाँ पे हमें सिर्फ residues find करने के लिए बोला है. Now if you observe the residue for we have to calculate the residue for this points z is equal to minus 1, z minus 2, minus 3. Okay, the given function has the simple poles. The given function f of z, the given function f of z has simple pole at z is equal to 1, z is equal to 2 and z is equal to. So we will calculate the residue at z is there, therefore residue at z is equal to 1. क्या है हमारा फॉर्मूला? रेसिड्यू एट z is equal to 1 for a simple pole. Limit at z tending to 1 tends to a into z minus a into f of z. f of z है हमारा z cube upon z minus 1 into z minus 2 into z minus 3, right? So here you will get, so limit as z tends to, here you will get z is equal to 1, put z is equal to 1, so you will get the residue for that point 1 upon 1 minus 2 is minus 1 and 1 minus 3 is minus 2, minus 1 into minus 2 plus 2, so limit as z tends to 1, so residue for this point is 1 by 2. I hope you are clear, because z is equal to, it's a very simple example. So residue at z is equal to 1 is the simple pole. Okay. Now see, we will calculate the residue at z is equal to 2. So residue at z is equal to 2 क्या होगा? Limit at z tends to a is equal to 2 है यहाँ पे, z minus a, so z minus 2 into z cube upon z minus 1 into z minus 2 into z minus 3, right? So z minus 2, z minus 2 get cancelled out. Now put z is equal to 2. So you will get at z is equal to 2 here. So 2 cube. 2 cube is 8. 8 upon here 2 minus 1, 1. 2 minus 3, minus 1. So here you will get minus 8. Yeah. Now residue at z is equal to 3. So limit as z tends to 3, z minus 3 into z cube upon z minus 1 into z minus 2 into z minus 3. So obviously you will get this. So put at z is equal to 3. 3 cube is 27. 27 upon, here we will get z minus 1. 3 minus 1 is 2 into 3 minus 2 is 1. So 27 by 2 is the final answer. So residue at, find the residue of at each pole is 27 by 2. So each pole, now it's a simple pole. So example is very simple. This is the first example on the residue. So this is very simple example. Let's move on the next example. क्या करना है हमें यहाँ पे? Evaluate the following integral using residue theorem. So first we have to find out the residue for this. Okay, so you find out the residue for this and then evaluate by using residue theorem. So first we will write down the residue theorem. What is your residue theorem? Integral over c f of z dz. Residue theorem we can write first. So residue theorem is f of z close integral over c f of z dz 2 pi I into sum of the residues. Sum of residues. Okay, at z is equal to a. Here, the poles of the function f of z are, how we can calculate the pole? So keep the denominator equal to 0. Equate the denominator equal. The poles are, so here you will get, which implies z is equal to 0. 2 minus z is equal to 0. So which implies z is equal to 2. Here the poles are, poles of f of z are z is equal to 0 and z is equal to 2, which is simple, which are simple pole. So we will calculate the residue for each pole. So residue of f of z at z is equal to 0. So we'll get residue of f of z at z is equal to 0. So limit as z tends to 0 into z minus 0 into f of z. f of z क्या है हमारा 1 plus z upon z into 2 minus z. Okay. So you will get here z cancel out. So 1 plus z upon 2 minus z. So put z is equal to 0. So obviously it is 1 by 2. Okay. Exactly similar way we can calculate the residue of f of z at z is equal to 2. Right? At z is equal to 2, which is equal to limit as z tends to is equal to limit as z tends to 2 into z minus a, z minus 2 into f of z. So here f of z is 1 plus z upon, okay, here your z 1 plus z upon, you will get if you see, we will find out the residue only for the points which are lies inside the curve C. But here you are, so no need to find out the z is equal to 2. Residue for z is equal to 2. Why? Because z is equal to 2 lies outside the curve C. रेसिड्यू थ्योरम हमारा किसके लिए है? Only for the poles lies inside the curve C. Now see here, you are having mod of z is equal to 1, right? So mod z is equal to, it means this is a circle with center at 0 0 and radius 1, right? So you will get this is a circle with center at 0 0 and radius 1, and z is equal to 2 lies outside the curve C. So it is no need to find out the residue for that. So therefore by residue theorem, in closed integral over C f of z. So f of z क्या है हमारा 1 plus z upon z into bracket 2 minus z dz is equal to 2 pi I into bracket residue of f of z at z is equal to 0 is 1 by 2 to 1 by 2, right? So you will get it is pi I. So residue theorem, by using residue theorem, the integration is, evaluation of this integral is pi I. Okay. Evaluate integral over C 12z minus 7 upon z minus 1 bracket square into 2z plus 3 dz, where C is the circle at z is mod of z is equal to 2 using Cauchy's residue theorem. Evaluate the integral over C 12z minus 7 upon z minus 1 bracket square into 2z plus 3z, where C is the circle mod z is equal to 2 using Cauchy's residue theorem. Okay, first we will find out the poles and we'll check whether the poles are lies inside the curve C or not. Okay, so first of all we will see the curves. Mod z is equal to 2, the circle with center at, the circle with center at 0, 0 and radius 2, right? Radius 2. Now we will find out the pole. So z minus 1 is equal to 0. So z is equal to 1. And z2z plus 3 is equal to 0, which implies z is equal to minus 3 by 2. That is minus 1.5. So obviously both the poles are lies inside the curve C because radius is 2. So obviously both the points lies inside the curve C. So we can use the Cauchy's residue theorem. For that we will find out the residues at z is equal to 1 and z is equal to minus 3 by 2. So first of all, z is equal to minus 3 by 2 is a simple pole. Here we can write z is equal to minus 3 by 2 is a simple pole of order 1, or z is equal to simple pole only because it's simple because it is having order 1. Okay, z is equal to minus 3 by 2 is a simple pole. Therefore residue at z is equal to minus 3 by 2 is, here you will get integral over c, z is equal to minus 3 by 2 is simple pole, z is equal to minus 3 by 2. Here z minus limit as z tends to minus 3 by 2 into z minus 8. So z minus 8 means z of z minus 8 means plus 3 by 2. It means 2z plus 3. Obviously it is 2z plus 3 into f of z is 12z minus 7 upon z minus 1 bracket square into 2z plus 3. Right? So here 2z plus 3, 2z plus 3 get cancel out. Now put z is equal to minus 3 by 2. So if you put z is equal to minus 3 by 2, so you will get here at z is equal to minus 3 by 2. So here you will get z is equal to minus 3 by 2. So put 12 into minus 3 by 2 minus 36 by 2. 2 cancel out, 2 6 minus 18 minus 18 minus 7 minus 25 minus 3 by 2 minus 1 minus 3 by 2 minus 1 minus 5 by 2. Here is minus 5 by 2 minus 5 by 2 square. So 25 by 4. So it is 25 to 4 minus 4. 25 by 4 minus 25 upon 25 by 4 into 4. So 25, 25 cancel out. So residue at z is equal to minus 3 by 2 is minus. So you can cross verify it. Z is equal to minus 3 by 2. Put here z is equal to minus 3 by 2. So 12 into minus 3 by 2. So here is minus 18, minus 18, minus 7, minus 25. Minus 3 by 2 minus 1 minus 5 by 2 square. So that is 25 by 4. That will get here minus 4. So residue at z is equal to minus 3 by 2 is minus 2. Exactly similar way we will calculate the pole of order 2. Okay. So here z is equal to pole of order 2. So you will get, and we'll calculate pole of order 2 here. We'll get here check once again residue at minus 4 and into minus 3 on 8 minus calculate pole z is equal to 1, right? Or pole z is equal to 1 of order 2. Of order 2. So here n is equal to 2, right? So we can calculate the pole for order n is equal to 2. Residue at z is equal to 1 is equal to 1 upon n minus 1 factorial, right, into d raised to n minus 1. So 2 minus 1, that is d by dz, to z minus a to n 2 into f of z. F of z is 12 z minus 7 on z minus 1 bracket square into 2z plus 3. Z minus 1 bracket square into 2z plus 3, right? Ultimately you will get here, cancel out. Now take the derivative of this with respect to z. Here 1 upon 2 minus 1 factorial, it means 1 by 1, that is 1. So d by dz of this, d du, so 2z z plus 3 to derivative of 12z minus 7, 12 minus 12z minus 7 into derivative of 2z plus 3, that is upon z plus at z is equal to here z plus 3 at z is equal to 1, right? At z is equal to 1 you will get this z plus 3 to 12. So put z is equal to 1 here. Z is equal to 1. So 3 plus 2, 5. 5 into 12, 60 minus L is equal to 1. Here is 1. 12 minus 7, 5. 5 into 2, 10. Upon Z is equal to 1. Plus 3, 5. Minus 10, 50. 50 by 5, that is 10. So residue at, here you will get residue at is equal to square, na? V square. 2 upon V. So V du minus U dV upon V square. 25. So 10 by 20, 50 by 25. Equal to 1 by 20. That is, we get the residue at z is equal to 1 is 2. So by residue theorem, we have closed integral over c 12z minus 7 upon z minus 1 bracket square to 2z plus 3 dz is equal to pi I to sum of the residue at z is equal to 1 and at z is equal to minus 3 by 2. So at z is equal to 1 is 2 minus z is equal to minus 3 by 2 is minus 4. Here minus 2 into 2 pi I minus 4 pi I. Okay, pi I is the final answer. Hope you are clear here to evaluate the Cauchy's integral. Cauchy's integral by Cauchy's residue theorem. How to evaluate this? Okay. Next one. Evaluate integral over C. Z cube upon Z plus 4. Z cube into Z plus 4, where C is the circle, mod of Z is equal to 2. Where C is the circle and mod of Z is equal. First of all, we will here find out the integral here by using, so you can use here Cauchy's integral theorem, Cauchy's integral formula, or by Cauchy's residue theorem. So what I will do, I will use here Cauchy's residue theorem. Okay. Now see, first of all here, so this is a circle with center at f of z is analytic everywhere. F of z is analytic everywhere except or except within and on the curves z, z cube into z plus 4 is equal to 0, apply z cube is equal to 0 and plus 4 is equal to 0, apply z 0 and z is equal to minus. Now if you observe here, so z is equal, this is a circle with center at the mod z is equal to 2. When mod z is equal to 2, so it is a circle with center at 0, 0, circle with center at 0, 0 and radius 2. Circle with center at 0, 0 and radius 2. So here you will get circle with center at 0, 0 and radius 2. It means the circle with center at 0, 0, radius 2. Here, right? Here is minus. Right? So obviously z is equal to minus 4 lies outside the curve C. So we will not find out the residue for that point. Okay, because it lies z is equal to minus 4 lies outside the curve C. Outside the curve C. So we will find out only for the residue at z is equal to 0. Okay. So at z is equal to 0 is a pole of order 3. Right, which is not a simple. So here z is equal to 0 lies inside the curve C. Okay. तो हमारा रेसिड्यू थ्योरम क्या बोल रहा है कि अगर inside the curve C है then only find out the residue. So z is equal to 0. So z is equal to 0 is a pole of order. Z is equal to 0 is a pole of order 3. There is a pole of order 3. Therefore, residue of f of z at z is equal to 0 is, limit as, here you will get 1 upon n minus 1 factorial. So 3 minus 1 factorial into e raised to n minus 1. So 3 minus d square upon dz square into f of z into z minus a bracket raised to n into f of z. f of z क्या है हमारा? dz upon z cube into z plus 4. Z upon z cube into z plus 4 at z is equal to 0. So here 1 upon 3 minus 1 2 factorial. So here is 1 by 2. There is d square upon dz square into z minus into z cube into 1 upon z cube. So z cube to z plus 4. At z is equal to 0. So this z cube get cancelled out. Now put z is equal to 0 here. 1 upon z plus 4. So first of all put 1 upon z plus 4. we'll evaluate the z plus 4 two times by 2 into. You will get the evaluation of dz square. So d by dz of. So we will get again d by dz of by dz of here 1 upon z plus 4 and z is equal to 0. Right? Get here 1 by 2 into by d. Here derivative of 1 upon z plus 4 is minus 1 upon z plus 4 bracket square into derivative at z is equal. Now again you will evaluate 1 by 2 into d plus 4 0 by 2 into derivative of this with respect to z plus 4 minus to 1. Derivative of z plus that is 1 at z is equal to 0. Right? Get here 1 by 2 into 2 upon z plus 4 raised to at z is equal to 0. Get 2 get cancelled. Put z is equal to 0. Get 1 by 2. The 1 by 2 into 2 upon 4 cube. This 2 out 1 upon 4 cube is 1 by 6. You add z at z is equal to 0 is 1 upon 60. Get it is 1 upon 64 by Cauchy's residue theorem integral over c z upon z cube into z plus 4. Z upon z cube into z plus 4 is equal to 2 pi I. You bracket sum of the residues, that is 1 upon 6, 2 upon 6, so 1 by 32 pi I. The final answer. I hope you are clear. Evaluate the Cauchy's residue theorem. Evaluate. Here we have to evaluate closed integral over c. Closed integral over c sin 2z upon z plus pi by 3 raised to 4, where sin 2z upon z raised to pi by 3 4. So here you can evaluate this theorem by using either by using Cauchy's integral formula or by using Cauchy's residue theorem. Only evaluate is given, so you can use any formula to evaluate this, either by Cauchy's integral theorem or by Cauchy's formula. So which integral we will use here? Sin 2z upon z plus pi by 3 raised to 4. So if you find this is the here again you will get the residue at z is equal to minus pi by 3 of order 4. अब वो भी कर सकते हो, minus pi by 3 it means here you will get minus 6 where mod of z is equal to 2. Better we will evaluate this by using the Cauchy's integral formula. Okay, that will be very simple. Can you see in this session we will see how to find out the complex integration or how to evaluate the complex integration. अभी हमने Cauchy's residue भी पढ़ा है, but if the finite number of poles are there, then it is very easy to use the Cauchy's residue theorem. And if the finite poles are not there, then we will use here Cauchy's integral formula. Okay. So here mod z is equal to 2. So this is the circle with center at 0, 0 and radius 2. Okay. Now we will check whether the given function f of z, the given function f of z is analytic everywhere, is analytic everywhere except analytic everywhere except at z is equal to minus pi by 3. Except at z is equal to minus pi by 3. So z is equal to minus pi by 3 is a pole of order 4. Pole of order 4. So by Cauchy's integral formula, obviously z of order 4. So mod of pi by 3 is less than 2. Obviously it lies inside the curve C. Right? Z is equal to minus pi by 3. So pi by 3 is always less than 2. So which is lies inside the curve C. Okay. So as it lies inside the curve C, you can see here by Cauchy's integral formula. Cauchy's integral formula will get integral over C, close integral over C, sin 2z upon z plus pi by 3 raised to 4 dz is equal to 2 pi I into 1 upon, here n is equal to 3. So n minus 1 factorial, right? So 4 minus 1 factorial into, here we'll get f raised to 4 minus 1 at a equal to minus pi by 3, right? Ultimately this will give you pi r on factorial is 6 into f raised to n at a. So here f of z is equal to f raised to f raised to 3 at minus pi 3, right? So here f of z is equal to what? Sin 2z. F of z is equal to sin 2z. Here f dash of z is equal to cos 2. F double dash at z is equal to 4 minus 4 sin 2. F triple dash at z is equal to minus 8 cos 2, right? Minus 8 cos 2z. So f triple dash at minus pi by 3. Minus 8 into cos of 2 into minus pi by 3. Theta is cos 2 into pi by 3. So cos pi by 3. Here you will get cos 2 pi by 3 and directly integral over c sin 2z upon z plus pi by 3 bracket raised to 4d is equal to here 2 pi I upon 6, 2 by 3, by 3 1 by 3. So pi by 3I into f third dash at minus pi by 3 is to minus 8 cos pi by 3, cos 2 pi by 3. So you will get cos 2 pi by 3 is 1 by 2. 1 by 2, that minus sign it absorbs. So minus 8 to pi by 3. 2 pi plus pi by I 2 minus plus 8 by 3. 8 pi I by 9 by 3 to 8 I into 1 by 2. Here 1 by 2, no? 8 pi I into 1 by 2. 4 pi I by 3. Your final answer. 4 pi I by 3. Evaluate integral over c z plus 2 upon z plus 1 bracket rest 2 and z minus 2 where c is the circle and z of minus I is equal to. So you can use this by using Cauchy's integral theorem also and by using Cauchy's residue theorem also because there are finite numbers. Okay, so first we will see whether the points are lies inside the curve C or lies outside the curve C. Okay, so here you can put Z is equal to here. So for the given curve, mod of Z minus I is equal to 2. Okay, for the mod of Z is equal to minus 1 and Z is equal to 2. Right, so Z of minus 1 get Z is equal to minus 1 minus I is equal to square root of this mod of this plus 1 is less than 2. So obviously Z is equal to minus 1 lies inside the curve C. Z is equal to minus 1 lies inside the curve C. Z is equal to minus 3 lies inside the curve C. Now, and here Z is equal to put Z is equal to 2. So 2 minus I is equal to, you will get square root of 4 plus 1 root 5. Obviously it is greater than 2. So Z is equal to, here Z is equal to 2 lies outside the curve C. The curve. So we will find out the residue at Z is equal to 1 only. But Z is equal to 1 is a pole of order 2. We will find out residue. Find residue at Z is equal to 1 is a pole of order 2. We will get residue at Z is equal to 1 of f is here 1 upon n minus 1 factorial 2 minus 1 factorial 2 d by dz z minus 1 plus 1 it raised to n plus 1 brackets into f of z. F of z, your f of z is z plus 2 upon z plus 1 bracket square into z minus at z is equal to 1. Right? Plus 1 the cancel 1 upon 1 minus 1 get d by dz of z plus 2 upon z minus 2, right, at z is equal to 1. So z plus 2 at z minus 2, so you will get here differentiate with respect to z. So z minus 2 into derivative of z plus 2 with respect to z is 1 minus z plus 2 into derivative of z minus 2 with respect to 1. So upon here z minus 2 bracket square, okay, at z is equal to at z is equal to 1. So you will get here z minus 2 minus z minus 2 on z minus 2 brackets. Z plus z minus z cancel out. Minus 4 equal to minus 4 upon z minus 2 brackets at z equal to 1. Z is equal to 1, it means here 1 minus 2 minus 1 square plus 1 minus 2. Residue at this is minus 2 at z is equal to 1 is minus 2. Then we'll get by Cauchy's residue theorem we get integral over c z plus 2 upon z plus 1 bracket square z plus 2 upon brackets into z minus 2 dz is equal to 2 pi I into sum of the residue. But here residue is minus because z is equal to z is equal to 2 lies outside the curve C. So we will not find the residue for z is equal to 2. Right? So here you will get minus 8 pi R. The final answer by using Cauchy's residue theorem. Evaluate the integral over curve C e raised to minus 2z upon z minus I. E raised to minus 2z upon z minus I bracket raised to I bracket raised to 2 where C is the curve mod of z plus I is equal to 1. Where mod of z plus I is equal to 1. तो सी e raised to minus 2z है. अब यहाँ पे भी पोल सी finite number of poles नहीं है, only one pole है. So we can use any theorem here. First of all, check whether the point lies inside the curve C or not. If it is not lies inside the curve C, then for z is equal to I, can take for z is equal to I is a pole of order, the pole of order 2. Z is equal to I in the pole of order 2. So you will get here, but first of all check whether Z is equal to I lies inside the curve C or not. Mod of Z is equal to I, so I plus I equal to mod of 2I equal to 4 greater than 1. Obviously Z is equal to root of 4 which is equal to 2. Root of 4 equal to 2 greater than 1. So obviously Z is equal to I is a pole lies outside the curve C. Outside the curve C. Because your circle curve is mod of Z plus I is equal to 1. It means this is the circle with center at x plus iy plus 1. Here you will get x plus iy plus I means here y plus 1. Circle with center at 0 minus 1 and radius 1. The circle with center at 0 minus 1 and radius 1. So obviously the point z is equal to I lies outside the curve C. Right? The point lies outside the curve C. Therefore, एक ही point है वो भी outside the curve C हो रहा है. So by Cauchy's इंटीग्रल थ्योरम, यहाँ पे हम लोग इंटीग्रल थ्योरम यूज करेंगे. तो जो भी पॉइंट है जो आउटसाइड द कर्व सी लाई हो रहा है, तो डेफिनेटली दैट पॉइंट by Cauchy's integral theorem, as z is equal to I lies outside the curve C. So you will get by Cauchy's integral theorem, the integral value is 0, right? Z is equal to 0. Directly you can write here the value of the integral is equal to 0 if it is lies outside the curve C. Evaluate the integral over curve C cos pi z upon z into z plus 2 into dz, where C is the circle, mod of z plus 3 minus I is the circle, mod of z plus 3 minus I is equal to 1, is equal to 1. तो जो भी आपका इंटीग्रल आएगा इट इज टोटली डिपेंडिंग अपॉन व्हाट, इट इज टोटली डिपेंडिंग अपॉन योर curve C, whether it lies inside the curve C or outside the curve C. Z plus 3 minus I is equal to, that is no, not 1, here is 3. So mod of Z plus 3 minus I is equal to 3. तो क्या हो जाएगा यहाँ पे, evaluate this cos pi z upon z into z plus 2 into dz, where C is the circle, mod of z plus 3 minus I is equal to 3. So check whether the given point z is equal to 0 or z is equal to 2. So you can calculate the residue also for that. I check whether the given point lies inside the curve C or not. So first of all, for z is equal to 0, there are two poles, no? Z is equal to 0 and z is equal to minus 2. So for z is equal to 0, we can check. For z is equal to 0, whether it is lies inside the curve C or not. Plus 3 minus I is equal to, now take the modulus of this, 3 minus, so you will get the modulus of, real part is 3, so square and minus square, so plus 1, root of 10. Obviously root of 10 is greater than 3, ADSR, so root of 10 is greater than 3, so the point z is equal to 0 lies outside the curve C, outside the curve C. Okay. For z is equal to minus 2, check for z is equal to minus 2, minus 2 plus 3 minus I is equal to square root of, here 1 square plus 1, that is root 2. Root 2 is less than 3. So obviously here z is equal to minus 2 lies inside the curve C. Obviously the curve lies inside the curve C. Okay. Here z is equal to minus 2 lies inside the curve C. So we can use, find out the residue for z is equal to minus 2. So we will calculate the residue at z is equal to minus 2. Calculate residue at of z at z is equal to minus 2. And if you observe z is equal to minus 2, it's a simple pole. So we can find out the residue as limit as z tends to 2 tends to minus 2 to z minus a into f of z cos pi z upon z plus z into z plus 2 cos pi z upon z into z plus 2 allowed. So limit as z is equal to minus 2 cos of minus 2 pi upon minus 2. Cos of minus 2 pi you will get here, cos of minus 2 pi to 1. Okay. Cos of minus 2 pi, cos of minus 2 minus minus pi is right. Cos pi is equal to minus 1 raised to n is equal to 1 by minus here. Okay. By Cauchy's residue theorem, Cauchy's residue theorem, right? Integral over C cos pi z upon z into z plus 2 cos pi z upon z into z plus 2 dz is equal to pi I into sum of the residues minus, here you will get minus pi I. Your answer here minus pi I. Okay. Correct. Here we can find out by using Cauchy's theorem how to evaluate the integral. I hope you are clear here how to evaluate the any integral by using either by using Referral theorem, either by using Cauchy's integral formula, or anything you can use here to evaluate the given integral. Now see, we will take one more example here to evaluate this. Suppose evaluate here next example, like evaluate. Now you think here, evaluate integral over c e raised to z upon close integral over c e raised to z upon z plus 1 into z plus 2 dz, where C is a circle with z plus 1 is equal to 1 by 2. And C is a circle with z plus 1 is equal to 1 by 2. It is a circle with center at here plus I by x plus minus 1 0. So this is the circle with center at minus 1 0 and radius 1 by 2. We'll find out these points. So here is a f of z is having a pole. Of z is analytic everywhere except at z plus 1 is equal to 0, z plus 2 is equal to 0, z is equal to minus 1 and z is equal to minus 2 are the poles, are the simple poles, right? But we will check whether it is lies inside the curve C or not. So for z is equal to minus 1 is equal to minus 1 plus 1, it is 0. So is less than 1 by 2. So z is equal to minus 1 lies inside the curve C. Equal to minus 1 lies inside the curve C. Equal to minus 1 lies inside the curve C. And here z is equal to minus 2. Check. Z is equal to minus 2. So minus 2 plus 1. Curve is here mod of minus 1, that is 1. So again, which is greater than by 2. Right? So z is equal to minus 2 lies outside the curve C. Z is equal to minus 2 lies outside the curve C. Z is equal to minus C lies outside the curve C. So here we can take as Z is equal to minus 2 lies outside the curve C. So we will find out the residue at, solve this integral by using residue theorem, which is simple. So we will find out residue at Z is equal to minus 1 only. Residue at residue of f of z at z is equal to minus 1, right? At z is equal to minus 1, so you will get here limit as z tends to minus 1 to z minus of minus 1, that is plus 1, to f of z. F of z is e raised to z upon z plus 1 into z plus 2, right? Z plus 1, z plus 1 cancel out, so raised to minus 1. That is equal to minus 1. So e raised to minus 1 upon minus 1 plus 2 to 1. Get here 1 by e. Residue of f of z at by e. By Cauchy's residue theorem, cannot find the light because it is light Cannot find the residue at z is equal to -2 because z is equal to -2 lies outside the curve C. So by Cauchy's residue theorem, we get integral over C raised to z upon z plus 1 into z plus 2z is equal to here 2 pi I into residue at this equal to 2 pi I upon is the value of the given integral. Okay. I hope you are clear here how to evaluate the integral when the given points, given the curve C is given. I hope you are clear here the complex integration. In the first two lecture, we have seen how to evaluate the complex integral by using Cauchy's integral theorem, Cauchy's integral formula, and also we have solved the CR equations. Also, we have solved the examples on Cauchy's Riemann equations, Cauchy's integral theorem, Cauchy's integral formula. So, I hope you are clear. You can solve any example on this Cauchy's integral theorem, Cauchy's integral formula, or Cauchy's residue theorem, or any example on Cauchy Riemann equation. Okay. So, if you are liking my videos, please do like, share, and subscribe so much. I will be here the next lecture the same time. So much.